In this video, we're going to continue our earlier work where we found relationships with exponentials and the oscillating behavior in our spring mass system. Our first observation was that when we looked at this simple differential equation, second derivative of x is equal to negative x itself, well, there are two forms of the solution. One was coses and sines, and that was sort of the natural oscillatory behavior we expected out of a spring mass system where things sort of oscillate back and forth forever. But we also found mathematically that we could solve the equation or find a solution to the equation with e to the it in exponential form as long as we had the definition that I squared was equal to -1 or I is equal to the square root of -1. If we allowed ourselves that imaginary constant, then these two exponentials were also solutions. A follow-up relationship was that when we looked at complex numbers and we looked at multiplying them, what happened when we did that was we ended up adding the angles involved with those complex numbers. Well, exponentials also turn multiplication into addition if we look at the exponents, so this is a hint again that there might be a relationship with complex numbers and exponential functions. That brings us, in a nutshell, to Euler's formula. Euler's formula captures that relationship between the complex exponential and the two trig functions we know and love, cos and sine. The only ingredient that looks complex on this side is a simple multiplier of I. And hearkening back to earlier in the course, this is so much like where we started this course at cos theta, sine theta, defining a parametric curve around a circle. It's the same mathematics underlying all of this. Now we're just adding an extra layer of interpretation and deeper connections to the kind of physics equations that we're going to be interested in looking at as we go forward. But if you look at this diagram here, the cos theta is the x-coordinate, the sine theta is the vertical component on a unit circle, only now we're interpreting the cos theta as being in the direction of real numbers, and the sine theta is being in the direction of imaginary numbers in the complex plane. Why is that relationship the way it is? Well, it's, again, just from the unit circle. If we have a length 1 complex number, magnitude 1 complex number, and we break it down into its two components, its Cartesian form, we're going to get the cos of the angle here being the x-coordinate or the real component, and the vertical component being the sine of that angle, and we indicate that in the complex plane with the letter I. So geometrically, looking at the pictures, there is no difference at all between what we saw earlier in the course and what we're seeing now. The only difference is we can do things with the I that we couldn't do with simply x and y coordinates that were considered completely independent. So first let's get some practice working with the complex exponential just as a thing. Our first observation is to note that the polar form that we introduced for convenience essentially with the magnitude or length and the angle separated by this little angular notation turns out to be exactly equal to what we would mean by magnitude times e to the I theta. Going back to the diagram for a moment, this is the angle we talked about. This was equal to the argument of some z value, the angle between the positive real axis and the complex number we're working with. And that's exactly what we mean here by e to the I theta as well. So when you see this in the wild now, you should interpret it as a magnitude plus an angle of theta. The e to the I part, that indicates that you're talking about an angle in the complex plane. Let's just do some quick examples to help reinforce that. If we draw our regular axes here, real line and the imaginary axis, and we're talking about the number I, well, that is exactly 1 unit high in this direction here. And so the magnitude of z is simply 1, and the angle is measured from this axis over to here is pi over 2. So z equals I is also equal to 1 times e to the I times pi over 2. If we wanted to work our way back with Euler's formula, just for checking, e to the I times pi over 2 is equal to cos of, and again remember the e to the I is sort of the indicator of angle. We just put the angle itself inside the cos theta and sine theta. So we're going to have cos of pi over 2 plus I times sine of pi over 2 Then if we check our values for cosine sine at 90 degrees, this is 0, this whole thing is 1, and so yes indeed, we get ourselves back to I using this formula in reverse. And again, geometrically, we're just working back and forth with the unit circle between angles and lengths and components in the x and y axes, or real and imaginary axes. A couple more just for practice. We have 2 real, imaginary, 2 in the positive sense, and then 2 negative in the imaginary direction. 2 and minus 2. The magnitude of that z value is going to be the square root of 2 squared plus negative 2 squared. That's 4 and 4. That is square root of 8. And the angle for that, or the argument for that, let's actually write it as argument of z. It's easier to interpret that rather than the angle, which might look like an L or something else. There's 2 ways we can do this. One is sort of the shortcut way, which is just take negative pi over 4. Or we could alternatively go all the way around here. That would be 4 pi over 4. That'd be 7 pi over 4. So here that would equal negative pi over 4 or 7 pi over 4. So as with any circular motion structure, there's multiple answers. We could also go 15 pi over 4 or other ones. We could certainly do those. Typically we stay within plus or minus 2 pi just to keep our lives simple though. If you take a complex analysis course in second year, some of you, Apple Math and I think EngPhys, you'll study this in a lot more detail. But for now, we can just find an angle that works. So z here can be rewritten as the square root of 8 times e to the I negative I pi over 4. Or, if we prefer, z equals root 8 e to the I times 7 pi over 4. Let's make our pi look more pi-like here. There we go. Either one of those is fine. They are in fact equal. Why? Because we go back to the formula from Euler. If we change the location of our angle by 2 pi, we get the same value back. So if we went through Euler's formula on this, we would get the same value from both of these answers here. All right, last but not least, as in a quick example, what if we had 7i, again, real and imaginary. If we went down to negative 7i, that would be down here. And so that's negative 7. The magnitude of that is positive 7. The argument of it, the angle of it, again, we have choices. Let's just do the negative pi over 2 version. We could also have done 3 pi over 2 if you prefer, though. The argument of z is negative pi over 2. So z, which is equal to negative 7i, is also equal to 7 e to the I negative I pi over 2. Make sure we have our negative and I both in there clearly, and we're good to go. So in some sense, the construction here is all geometric. We just find an angle and we jam it into this e to the I form. What we see as a benefit is when we come to taking multiplications or products of complex numbers, if they're in this form, then we're going to use the fact that it's actually an exponential. Let's see how that works here. We have z equals I, and we won't go through the full details of this, but you should believe that z1 could also be written as 1 times e to the I pi over 2. Oh, I can't help sketching it. All right. I is up here, pi over 2 angle. There we go. And z2, because we're here, it would be, if it's negative 1, it is out here on the real axis to the left, and so it's an angle of pi. z2 is going to equal e to the I pi. Let's use direct calculations first, so just multiply and multiply. z1 times z2 is equal to I times minus 1, and that is equal to negative I. If we use the polar form, actually just put those into exponential, we can also put them into polar form with that little angle symbol. And here we go, this was just 1 angle pi. Then what we had here was 1 angle pi over 2 times 1 with an angle of pi, and our rule was multiply the lengths and add the angles. So here we just get 1 with an angle of 3 pi over 2. Well, that's sort of a weird thing to have to memorize. What we see when we tackle this with complex exponential is that we don't have to memorize anything. If you asked anybody what e to the I times pi over 2 times e to the I pi was, you would just think, oh, I use my exponential rules and I multiply this out. I would add up the exponents, plus I pi, and then we just tidy that up, taking the common factor of an I out, and then we'd have 3 pi over 2. And a quick check will tell us that all of these are exactly the same point. If we go 3 pi over 2 down here, that'll be the location at minus I. Oh wait, that's what we found with the Cartesian forms. That's exactly what we found as well for the complex exponential and the polar forms. So all of those approaches to multiplication can be used and give us, of course, the same answer, thank goodness. And that's going to be a surprisingly useful tool as we go to analyze this in the context of our differential equations.